Hello there! If you are here, that means that you are here for an algebra lesson. Ah, this is the way. This is the way. Let's get started. Oh, I guess we better get started. So, welcome to 6.1 of our next algebra lesson. So, let's make my face smaller. And I obviously haven't actually opened the lesson yet, but that's okay. So in this lesson, we are actually going to be exploring the rational exponents and nth roots. So up until this point, we've been talking about square roots, but it turns out you can actually do a lot of different things other than square roots. So here's our real world example. So we've got somebody looks outside that says it's cold outside, but we also see that it's windy. And so hopefully we all know here in Missouri that the wind chill can sometimes be worse than the actual temperature. So the actual temperature outside is 15 degrees Fahrenheit. The wind speed is 45 miles an hour. So what are some mathematical questions? What is the relationship between temperature, wind chill, and miles per hour? How fast is the actual wind going? I think it's got some information down here. So then they do give us an equation. So the wind chill is equal to all of this. But you'll notice some of this here, man, that looks like a tough equation to deal with. So we've got T, we've got our temperature, and we've got our velocity. How do we deal with a fraction in the exponent? So that's what we're going to talk about today. So let's get to it. So as I mentioned, we have seen things like square roots. That's something that we should be a little familiar with. And that's simply like, the example they have here, if you have the square root of 16, that stands for, what two numbers multiplied together gives you 16. And so we know that 4 times 4 is 16. But turns out you can actually do the root for any number you want. So for example, you've got, what is the cubed root of 8? So our square root, we have actually shortened, but really we could put a 2 right here. That shows the square root. So the cube root means what number multiplied together 3 times will give us 8. And so that's something that I just kind of know off the top of my head. You take 2 times 2 is 4 times 2 is 8. So you can actually take the root using any number. So that's where they're going to use the term n. So the nth root of a, they would write something like nth of a. So that's the algebra form of what we're talking about. So you can put any number in there for n. You can put 2, 3, 4, 6, 1 billion. That would be really hard to figure out, but you still could do it. So there's a couple of properties that we need to understand as we go through. So first of all, when n is even, so that's going to be something that we're used to. So like square root, let's draw that better. Square root, if we were going to do the fourth root, the sixth root. So all of these have a similar characteristics. And that is there are 2 real nth roots. So that means that you can write it something like that. But for instance, 3 to the power 4 equals 81. Get rid of this stuff. 3 to the power 4 equals 81, but also negative 3 to the power of 4 equals 81. So when you find these different roots, Like if you were to do the, uh, oh my gosh, the fourth root of 16, so that's going to equal plus or minus 2, because 2 times 2 is 4, times 2 is 8, times 2 is 16. But you can do that with a positive 2 or a negative 2, and you will get the same answer either way. However, for odds, when n is odd, so we're talking about the cubed root of something, that is not the case. So the cubed root, because it's an odd function, will only have one root. So, for example, they use 5 to the power of 3 is 125, but negative 5 to the power of 3 is negative 125. So the negatives matter in the cubed root, whereas in the even roots, you're going to have a positive or negative. So then we scroll down here, and we've got this interesting kind of question here. The steps shown demonstrate how to find the value of k for square root of a equals a to the power of k. So, oh, come on, pencil. So this guy right there. So this is kind of an interesting thing to look at. So given that square root of a equals ak, what does that mean? So if we want to get a by itself, we've got a square root, so we're just going to square both sides. That's what we're doing here. So then the square roots cancel out, and this side just stays the same. So that's where we're at. We've got a equals a to the power of k squared. So this part right here would just be like ak times ak, which is a to the power of 2k. A to no power is also the same as a to the first power. Okay, so then since this is a to a power and this is a to another power, those powers must be equal to each other. So we've got 1 equals 2k, so that means that k equals 1/2. So why do we do all that? So the square root of a is also equal to a to the power of 1/2. So that's a very useful thing to know, and as we move down, we will see that this creates a pattern. So let's do a couple of practice problems here. So what is the value of 81 to the power of 1/2? So 81 to the power of 1/2 is equal to 9, because 81 to the power of 1/2 equals the square root of 81. And remember, the square root is also kind of like having a 2 right there. And 81 equals 9 squared. So it works with 81 as well. So blah, blah, blah. So until now, we've been using our exponents as real rational numbers, or integers, I should say. But you can use fractions as your exponents as well. So rational exponents are defined so that the properties of the integer exponents apply also to them. Using the power of a power property, determine the value of k for cube root equals ak. So again, we're going to do the exact same thing that we did earlier, except this time with a cube root. So we've got cube root of a equals ak. So we're going to get rid of that cube root. So we're going to cube both sides. So we're going to cube that side. We're going to cube this side. So now our right side becomes a 3k, and our left side is just a. So this is going to cancel out. Or we could say a to the first power. So since it is a to the first power, we can say 1 equals 3k, or k is equal to 1/3. So we can put in there k equals 1/3. What did I do? So it worked with square root, it worked with cubed root. So can we make a rule out of it? So that's what we're talking about here. In general, for what value of k is square root, or nth root of a equals ak, assuming that nth root is a real number. So in that case, k is going to be equal 1 over n. So this is something that's going to be very helpful for us while using exponents. So let's see here. What are the values of negative 27 to the power of 1/3? So that's the same thing as cubed root. So if you think, so I'm ignoring the negative sign right now, but if you take 3 times 3 is 9, times 3 is 27, throw a negative sign in there. So negative 3, because negative 3 cubed is equal to negative 27. I didn't even do the 16 one yet. So 2, so this is the fourth root, or 16 to the power of 1/3. So 2 times 2 is 4, times 2 is 8, times 2 is 16. And there we go. So we did a couple of examples with numbers. So can we extrapolate that into a rule that we can use for any number? So that's what we're looking at for here. So in the first couple of numbers, we had our exponents a to the nth power, where our n was equal to 1. I'm sorry, that's not right. Where our m was equal to 1. 1/3, 1/2, 1/4, all that kind of stuff. But can we do something with both of those? And of course, the answer is going to be yes. So you can rewrite expressions, exponents, in the power of, or using the power of fractions in the exponent. So this is our magical little chart. This is basically everything we're learning in this chapter. So the exponent, so for any natural number n, integer m, and real number a, when the nth root of an a is real. Okay, so they're just being mathematically super precise. So let's translate. So the exponent mn, right here, indicates the mth power of the nth root of a quantity. So for example, so if we got 16 to the 3/4, that is the same as saying 16 cubed and 16th to the 4th root. So we get rid of all of that, and we have something that looks like this. So once you're here, you can pick whether you do this first or that first. It doesn't actually matter. You're going to get the same number. So in this case, they took the 4th root of 16, they got 2, and then they cubed 2, they got 8. So when I say you can do either or, when I say you can do either one first, that's what they're doing down here. So here they have negative 8 to the 2/3 power, so that one is the same as saying negative 8 squared and the whole thing to the cube root. So here they took negative 8 squared first, and then they took the cube root equals 4. So you can use this to your advantage when solving these problems. When one of them is harder than the other one, maybe doing them in a different order might help. So I really am not good at these roots. So if I see a number, a smaller number that I know is a root, I'm going to do that first. That is my personal preference, but in many situations, it's going to be, either one might be more handy than the other. So it's really handy to have that to use. So let's look at some examples. So Kyla and Jean use different methods to simplify. Kyla's method, so they're both working to try to simplify negative 27 to the power of 4 over 3. So Kyla's method looks like she did the cubed root first because negative 27, so 9 times 3, 9 is 3 times 3, so negative 3 times negative 3 times negative 3 is negative 27. So then once she got there, she took negative 3 to the power of 4 and got 81. Let me guess, Jean did it the other way around. So Jean's method, she took this inner negative 27 to the power of 4, got this big fat number, and I'm assuming she probably shoved that into her calculator and it pooped out that number, because who knows that off the top of their head. Later on in this video, I will show you how to do all of these with your calculator, so there you go. So let's see here. Down here, they're just matching which one did which method do you prefer. Again, it is going to be entirely your preference, and it might change based on the situation, but both methods are perfectly valid and work the exact same way. So we've got a couple more examples to try out. So it says you can rewrite algebraic equations with radicals as algebraic expressions with rational exponents and vice versa. Some examples are shown. So looks like we've got this thing right here. The fourth root of r cubed is the same as r to the power of 3 over 4. And example 2, so we started with a fraction in the power 2xy to the power of 5 over 3. So that's going to be equal to the cubed root to the power of 5. Or you can put the 5 on the inside. Again, it doesn't matter. It all works the same way. So let's see here. In example 1, if the result is a real number, can r be any real number? So since this is even, I would think that your possibilities for inside of r would have to be positive numbers. If you get, so same reason for square roots. Since it's even, you're going to have a positive number in the inside of there, or you won't be able to get anything to come out. So let's see what their sample answer is. Value of r cannot be negative because it is an even root. So I hesitated there for a minute because I forgot if it was this number that needed to be even or odd or this one. But I remembered square roots have to have, your normal square roots have to have, or can't have a negative on the inside of there without using an imaginary number. So that's kind of what saved me there. Another way to think about it. In example 2, if the result is a real number, can x and y each be any real number? I'm assuming yes. So since this is odd, you can have a negative underneath there, and then your answer would be negative as well. It's not a good day unless we have real-world examples, right? So if we look at some of the equations that we've actually already used a little bit, you'll see powers like blah 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 to the power of in a lot of different formulas. So some things that we've already seen: area, volume. So that's volume of the sphere, volume of a cube, all those things. You might have something squared or cubed. This has to do with a pendulum and how it swings. So you're going to have a lot of these powers and things like that in the real world. So let's look at one. So the basal metabolic rate for a mammal is the rate at which the mammal uses energy while at rest to maintain vital functions such as breathing. The function is that, known as Kleiber's law, relates a mammal's basal metabolic rate R in calories per day to its mass M in kilograms. Rewrite this function as a rational exponent using the rewritten function to compare the basal metabolic rates of dogs shown. Blah, 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 blah. So, okay, let's look at this thing. We've got a 73.3. So that is just your coefficient. So that's not going to change. But we have the fourth root of m cubed. So it doesn't matter whether that cube is on the inside of the fourth root or the outside. It's still going to be the same. And so that m is going to end up being m to the power of 3 over 4. So then we can use that. We can compare the mass of the small dog, which is 3.5 kilograms. We just plug that into here. Mass of the large dog is 37. Plug that in for m, and bam, we've got it. So this is what we already figured out. Why is it 3 over 4 instead of 4 over 3? The numerator of the exponent represents the power, and the denominator represents the root. Don't get those mixed up. So then we can compare the basal metabolic rates of the cat and dog, and one way to do that is to find a ratio for the metabolic rates. So basically, they want us to set them on top of each other and just find a ratio. So that might sound hard, but it's actually really not, because calculators are a great thing. So we're just going to figure out what this number is and what this number is. And I have a new way of showing it to you. So we've got 73.3 times 37 to the 3/4. And then we have 73.3 times 3.5 to the 3/4. So this should look something like your calculator. Of course, I wrote all over it because I needed to remember the numbers, but you know, life is the way it is. So if we're going to figure out that top number, and I'll write it somewhere else. Oh, no. There you go. So the way we're going to solve this guy right here is we're just going to type in 73.3, and hopefully by now you know that this is your power button to the power of. So we can push our little caret. And then now that we're up here, we can actually just shove in our fraction. But I'm actually jumping ahead of myself. So that's my bad. Oh, whatever. 73.3 times, or parenthesis, whatever you want to do. Now we're going to do it to the power of 3 divided by 4. get my face out of the way. So that one is going to be 1099.65. And then our bottom one, put on their face, is going to be 3.3 3.5 to the power of 3 divided by 4. That says 187.566. That is not anywhere close to what they got. Oh, yeah, so they canceled out these. So I'm willing to bet when I open my calculator again, I'm going to take, because they want a ratio, right? So it shouldn't matter. So I'm going to take my top number, 6, 5, 1, divided by my bottom number, 187. So I might be a decimal point off or something like that. But so 5.863. So they rounded it to 5.9. I'll agree to that. My lights went off. Oh, anyway. So that's one way that you can use your calculator. So make sure you know how to use that power button. It's going to make your life a lot easier. So how can you find the values of the powers in the numerator and denominator? I plug them into my calculator. And so the large dog's basal metabolic rate is about 5.9 times the smaller dog's basal metabolic rate. So there you go. Something for your biologists.